Morning, everybody. Thank you for the introduction here. Today, we're going to be talking about the gap elements and how to use them to approximate contact in your nonlinear analysis. So we're going to cover what gap elements are, how they function, how to define them, some additional considerations you may want to use in the nonlinear analysis to help the analysis run smoother. Definitely want to cover those limitations that you can run into because they're not actually contact elements. We're just using some springs. And then we're going to go through a couple demonstrations. So what are gap elements? To be more specific, they are simply just nonlinear springs. They are directionally dependent, so we can use this in either tension or compression, technically in both. So that advantage gives us the ability to use them as contact elements. Especially since solution 106 and 129 are nonlinear static and nonlinear transient, do not include or do not have the support for contact. We can even include static and kinetic friction. And what gives these spring elements a particular advantage is their variable stiffness. They are adaptive. And this is very important when used as contact because it'll ramp up the stiffness as that gap, if you're looking for gap or that direction, closes. So that avoids any sort of stiffness discontinuities and allows our analysis to proceed. So, more simplistically, I got a little example here on the right. We are looking at two nodes here, GA and GB. We are basically defining a connection between these two, a vector, and we're assigning a spring Ka to it. And this spring can function in either the negative x direction, assuming that we consider this spring along the x-axis, or it can function in the positive x axis. So no matter which way, in this particular example, if we're using it in the form of contact with the gap, no matter the path GB follows, once it closes that x direction, stiffness will then be applied and we'll have that contact behavior that we're kind of looking for. So gap elements are defined via two nodes. GA is the from node, GB being the to node. This creates a vector of GA to GB, and this is that element's x-axis. This is very important that we keep this understood correctly because this is the line of action in which compression and tension forms along. But like other line elements, we do need to define orientation. It can be defined a couple of different ways. We have vectors, or we can reference an existing node, and a local coordinate system can be used instead. This local coordinate system needs to have the x-axis positive and parallel to the gap element's positive x-axis. There's a couple of problems if it's not. If you have it reversed, you can have all sorts of interesting things happen. And if they're positive but not parallel, generally what I've seen is that the analysis will fail to converge when we reach that point where stiffness or contact is added to the analysis. However, some degree of out of alignment will still function appropriately. So to define the gap element, we've defined this in our property card here. Orientation of the coordinate system is really only important when you're using a local coordinate system, though you do need to use a local coordinate system when you're dealing with coincident gap elements because there's no physical length or distance between GA to GB. There's no way to for Nastran to identify that positive x direction, so we need a coordinate system. So that'd be defined here in the property. Max penetration gives us a value that will activate basically that adaptive stiffness that we need. Otherwise, we can have discontinuities in our stiffness in our analysis. So this is the minimum that we need to define in order for adaptive to function. The additional max adjustment ratios and penetration ratios just tweak when stiffness is added, as stiffness will be ramped up as the gap closes, assuming you have a gap. So we get over here to the property values on the left-hand side of the card. These are the important values that we need, that we're really looking for to get it to the gap element to function the way we want. Compression stiffness and tension stiffness, pretty straightforward. We recommend using roughly 1,000 times the Young's modulus of the material that you're using for the parts that you're having, that you're trying to create the supposedly contact between. Initial gap is openings are specified in this gap property card. They are not derived from that physical distance between GA and GB, so keep that in mind. So to then generate these gap elements, I'm going to talk about probably the most common way you'll use this when you're generating multiple elements between faces, edges, etc. And that would be using the Mesh Connect Closest Link. The advantage of this tool, it lets you select the from and to nodes to begin with, so you can explicitly select the GA nodes to the GB nodes. You do not want to use the coincident link here, as it only has you select both nodes at the same time, so the gap element definition will not maintain that consistent GA to GB orientation that we're going to find very important in the analysis. So orientation, once you've selected your nodes, you'll come up with this dialog box right here. And this is where we get to define the orientation for our element. We're just looking for defining the XY plane for our elements. And even if you're using a local coordinate system for like coincident gap, you still have to define an orientation right here. It won't let you pass this without defining some. So you can either define a node or a vector, for example, to use this. And if you're not using a local coordinate system, this will be very important to make sure that you select that appropriately. And here, one final little option here that I highly recommend. If you are modeling contact that has a physical gap in it, the gap options right here, adjust length, will automatically fill in that initial gap value here based off of the physical length or the physical distance between GA and GB. So I will actually demonstrate that in our model here. So I can't emphasize enough how important the selection process is when it comes from the from and to selection. It is important that that from to direction must align with the positive x-axis of whatever coordinate system you might be selecting, especially when you're dealing with coincident nodes here. So in my example here, imagine that these two are actually physically touching. So with them physically touching, I like to imagine them separated as they're drawn here in my lovely MS Paint art here. And as you can see here in the order based off the gap element, there is an order issue. We have our first element here is from 101 to 201. So this, with this little gap, we can see the direction is downward instead of the positive X direction that we have here from our local coordinate system. So because of that, we only have one element here, that's 202 to 102, that actually faces the right direction that we need. And we're going to run into problems with this particular models. So that's why it's very important to remember that GA to GB, your selection process is very specific. So generally, because of this, because of the directions that you want, using a coincident mesh is very important. You want those nodes to match and line up. And they're very important, especially when dealing with a gap. But we'll talk about that in an additional slide or in a future slide. So when it comes to the nonlinear analysis here, I do have a recommendation of creating multiple subcases. I generally follow this rule here where it's the first subcase is 1% of the load that I'm applying, ramping it up to 10%, then 100%. This gives you the advantage with Nastran to help it figure out which gap elements are open and which are closed, which refers to being active, and stiffness is being added. Another minor little thing that you might run into is because of the stiffness updates that are required with the gap elements, if you do not have enough increments or time steps in your analysis, you could run into some weird numerical issues with it in the way the contact will behave. So there's two ways you can get around that. Just either throw in enough increments to your analysis or modify the number of iterations before update. Downside of both ways is as you add more, it does slow down the analysis as you have to solve more iterations or increments. And so I like to reemphasize here that we're not actually dealing with contact elements. We're dealing with single directional springs here. So having our elements aligned and organized, making sure that they're as perpendicular to the intended contact face as possible will help avoid any sort of issues. In my little lovely MS Paint graphic here on the left, we have a variety of gap elements that are orientated in all sorts of different directions. And because the gap element is really only concerned about GB closing in on GA along this x-axis or our line of action, it creates this virtual contact plane. So GB can move somewhere over here and won't stiffness won't be applied until it reaches this zero distance along this axis here. So that can cause some problems with you, or problems with your model, with orientations being a mess like this, and can causes some limitation in how much deformation you can see in your model. And I'll demonstrate that in one of our exercises. So example of mesh matching and the importance of that. Screenshots are from Simcenter 3D, but the same issue can occur in Femap. So for example, here we're dealing with a cylindrical contact, like a pin or a bolt in a hole, for example. Even though we've got the same number of nodes here on the top left image, there's a slight skew to our nodes as compared to our center nodes. And what happens is that closest link can get a little funky. We can get some of these errant connections. And what happens is they'll end up fighting each other. And unfortunately, if one gap element fails to converge, your whole analysis is basically going to fail to converge. So a matched mesh, like we see here in the bottom example here, creates this nice uniform element direction and these easily understood contact conditions, like I showed in the previous one where we've got these infinite planes. So in this one, I used a radial or a cylindrical coordinate system to help define orientation. So let's jump into a demonstration here. So I apologize, I had to pre-solve or pre-set up a lot of things here. There's a lot of steps involved in order to get that nice, lovely matched mesh that we need into this. And due to time constraints, I had to do this in advance, because just going through the contact setup or through the gap element setups is going to take quite a bit of time here. So one of the things I like to point out first here is I do have two coordinate systems here that I will be using for orientation here. This is going to be for our coincident gaps. All of my planes for coincident gap are lined up with this particular direction here, so making it easier. And then I do have, for example, the bolted connection right here, in which I'm looking for contact between the shank and the bolt hole. We will be using gap elements with a physical gap with it, and I'm going to be using a cylindrical coordinate system with this one too, because it ends up being a little bit more reliable than other ways to define orientation. So let's jump into defining our contact here, or our gap elements. For example, I'm going to start off with this connection right down here at the bottom here, the underside of the bolt. And we're going to be looking at contact between these two faces here, or simulating contact between those two faces. Let's see here. I'm going to be using the draw erase tool to make things easier to select. So I'm going to reverse the selection. I've selected the bolt here, and what we're going to want to do is we're going to use that mesh closest, or connect closest link. We're going to be selecting that surface right here. Click OK. We're going to reverse. I'm going to be selecting this surface. Remember, this is in the direction. If there was a small gap, these two, the separation between these two would form that vector that's in that same positive x direction of this local coordinate system I'll be using. It also happens to line up with the positive z-axis of the global. So click OK. I do not have a property defined here yet. We're going to this coordinate system here, I haven't found a particular use for it. It doesn't really matter, because if we're defining it here in our spring element or gap element, let's change this to what we want. Let's name this coincident gap. We're going to put a value here. This is where we're in the inch unit system here. This is steel. I'm just going to use a value of roughly 1/e to the 12. I like to add a small value here in the tension stiffness of like 1, Nastran does automatically add one. It's a very small value. I believe it's somewhere around 1e to the negative 14 times this value here, whatever it figures out. And then I'm going to add a matched penetration value here. I get away with 0.1. I am roughly basing this off of my mesh size, my finest mesh size around here. You can drive this smaller, you can drive that a little bit larger. Get too large or too small, and you'll start running into convergence issues. So there we go. We've got our coincident gap. Oh, one last thing, almost forgot. Because this is coincident, I need that coordinate system here for that to function properly. I'm going to click OK. And then we're going to define I'm just going to click a node on here. There is a slight possibility of making a mistake. If I were to select one of these nodes right here that's part of this coincident gap, even though technically the gap element should be ignoring that and using the cylindrical coordinate system, Nastran is going to spit out a formatting error and be upset that a node for orientation is also the same node applied to either GA or GB. So we're just going to select some random node out here and click OK. So now we got our gap elements created. At this point, one of the things I really like to do, verify just to double check that I do actually have a coincident mesh. I like to turn off the elements and then just do a little rotate or motion of the model. You'll see that the icons for the gap elements disappear. And what we should be left with is any sort of physical length to the gap elements. Now, because this is coincident, there shouldn't be any physical length. So this rotation here just confirms to me that I do actually have coincident nodes. So it's just a double check because it's so easy to make that mistake or make an assumption and forget what you're doing. Oh, I like to leave this off here for this next bit. So now we're going to do between the two plates here. Let's get this orientation or the selected plate right. So again, we're going in that positive X1, so I want the lower plate surface here. Mesh, connect, closest link. Select that surface. Reverse these two. That surface. It's already using our coincident gap that we've defined. That one should be using the coordinate system. Again, I've not had this affect anything in the particular usage cases that I've had so far. So let's go to node. If you don't click on node and you just go to, if you'll notice if you're over here, by default, when this comes up, this node here is selected and you go hover over here and you forget to click on node, you're going to change one of the nodes that has been selected for the gap elements. And you're going to have an error to do that. I have made that mistake so many times and it's been so frustrating to do that. So let's turn on our mesh because we now need to select a node. I don't want to select anything on that interface because that'll create another problem. But again, just another random node. And I'll click OK. So now we should have our gap elements there. Again, I like to turn off the mesh just to kind of verify. Good, wonderful. Everything disappears. We could turn on our mesh. We're working with this again. So reverse, this is off. Perfect. This should be our bottom face. Previous command should be, no, it's not what I thought. We'll go back to mesh, connect, closest length, on surface. Just to verify that, see, we've got those nodes. Let's reverse our draw erase. Surface, again, we could just highlight C, go OK. Now we're going to use, oh yeah, sorry, we're still on here. Last coincident contact we're going to define. Just going to select that node right there and go OK. So that should be all three of our coincident contacts or coincident gap elements. You can see as I rotate this, everything just disappears. So that is wonderful so far. Now let's do our gap here. We've got a physical gap. Let's define that gap property just beforehand. We're going to call this just gap with gap. I have better luck with the cylindrical coordinate system than defining a vector. In theory, if I did a z-axis vector on that should be normal to all these gap elements here, and it should run just fine. But I find that gap elements can be kind of finicky sometimes, and that one may or may not want to converge on us. Fun stuff. I'm using basically the same values, 0, 1, everything. The only difference here is a cylindrical coordinate system that I'm going to use for orientation. Click OK. Cancel out of that. Now we should be able to define our gap. You notice that I left the initial gap blank. I'm going to take advantage of the tool in here and have it automatically figure that out for us. Oh, so it's off. Click, click. Okay, now we should be able to reverse this just to make everything that much easier. So we don't want this. We now want our gap with gap. I'm going to tell it to automatically adjust the length. I still got to give it a node. I'm going to select just some random node that I know that's not part of any sort of gap definition and click OK. So now it's generated it. Let's take a look. As I mentioned before, you can see the gap elements that are the coincident gaps disappear, yet our gaps with physical length still are there. And I could take a look at this and I just visually inspect it. Everything looks appropriate. That looks fairly radial to what I would expect, nothing errant. So I feel a bit more confident that this analysis is going to run successfully. Also take a look here. This is our gap element. This is our property that we originally made, but what it did is it created 2 new gap properties based off of the physical distances that it measured. The reason why it came up with 2 physical distances is because it's capturing mid-side nodes. The mid-side nodes are not they're not following the curvature of our hole right here. So that's why they're cutting into the hole's diameter a little bit. And so that's why we're getting 2 different values here. But they're small enough, I don't really care. We shouldn't have too much of an issue. I could have avoided that if I wanted to. Let's see. So with that, we've got everything defined. We are ready to set up our analysis and run it. Turn that, everything's visual. Let me get these loads and constraints turned on so you can see exactly what we're dealing with here. The model is fixed on either end, so each of these beams are fixed. We've got a symmetry plane here. Everything's constrained in that symmetry plane, and what we've got is an enforced displacement of 1 inch right here. We're going to put an enforced displacement on there. Let's jump over here. We'll go through part of the setup of the analysis here. So I'm just going to say we're going to do a new analysis. We're going to set this to nonlinear static. And what I normally do is just click OK because the defaults are usually fine. I've only got 1 constraint set and 1 load set, and it's going to automatically select that for us. We can see that right here. So then I would just jump into here, edit my nonlinear options here, say something like 100 increments. I'm going to leave this as default, and all our other convergence are fine, and just click OK. Now, I would go through, what you can do here is if you wanted to go through the steps of creating the subcases, we can go through that right here, for example. But we're not going to, for the essence of time, we're going to skip over that, so I apologize. And unfortunately, due to, no matter how much I worked on this model to try to shorten it down, it still takes a little too long to run the analysis here live for the demo. So we're going to jump right in and just assume that I set everything up correctly and take a look at this model here, so that you can see how contact has performed, or our gapped elements have performed. Let's hide the body here so we can start seeing. Let's turn on some displacements results here to visualize. We can turn off this to help make it a little cleaner. So here we go. We can see the behavior. We are getting the expected separation right over here, but both the underside of our bolt is definitely showing contact. And we're definitely seeing some contact over here. There is a little bit of penetration, but that's part of the contact's behavior. And we're definitely seeing some motion over here, but it looks like that stability stiffness that I added to it is kind of limited the amount of motion that we're seeing here. So I could try running this analysis again with an even smaller value, or just neglecting that particular aspect of it. This model is a little bit more statically stable due to the symmetry plane, but without the symmetry, when I was first running this model with this full bolt here, rotation issues were definitely a problem with this model. So you can see here, we're getting contact behavior in a matter that seems sensible or logical. So let's take a look at where this contact behavior might run into a problem here. So in this model here, I've got a very simple but poorly modeled cam and valve. It's just a simple 2D shell model, just to make this quick and easy to run through. This cam was going to move down and push onto it. I've got just a single gap element here right now, just to model the behavior. I figured it's enough just to demonstrate what we're going to see here. And so it's going to hopefully behave with contact in the way that we're expecting. So let's take a look at what goes on in this model as things move closer and closer. So we can see here, we now have what we considering contact or stiffness is applied to those gap elements, and now we're getting that behavior we're looking for. It's continuing on wonderfully. But watch as that node slips off the side of our valve, the end of our valve stem here. It's still continuing to push down on that element. And that's what I really want to impress upon when it comes to that infinite sort of contact plane that I was referring to earlier. Because technically we are not dealing with contact elements. These are just single directional spring elements. They really only care about that X direction, line of action. Doesn't matter whether it's off to the side. Once that X direction closes, stiffness is added, and we get our contact-like behavior. So this will continue to push down on this as this thing rotates. So keep this in mind with your behavior. Large deformations along the contact interface could have some potential problems like this. And you'll get some unrealistic effects. All right, that concludes our demonstration right there. So in summary, gap elements can be used to facilitate contact behavior in a nonlinear analysis. The use of adaptive stiffness will help avoid any sort of discontinuities in the stiffness matrix during the analysis. Should hopefully allow your analysis to succeed. If you run it without it, so far my experience is it's been nearly impossible to get to converge without that value in there. At least if you want it to behave like contact. Otherwise, you'll just get a spring being applied to it. Probably be a very soft spring. Direction of orientation, that line of action is very, very important. I can't impress upon you how important it is to get that appropriate and how much of a headache that will cause to you if it's not appropriate. And then also limitations with it. Again, we're not really dealing with contact here. We're dealing with one-dimensional spring elements. So it creates this virtual contact, this infinite contact plane when you get to this large deformation on that interface. And then also, unfortunately, I wasn't able to demonstrate it due to time constraints, but getting the mesh match is very important because it also affects the orientation of all our elements in the model. So with that, we're at any sort of questions here. Hopefully you've got a lot of questions. I know I had to cut a lot of this out for time. I could have talked for an hour on this and gone over all the different ways you could break this analysis.
So we do have one question here. It says, is it possible to use gap elements in nonlinear transient analysis for sliding contact?
You can use it in a transient analysis, like for example, that the cam shaft in, or the cam in valve was a transient analysis. It's not a problem. It's just more of the issue of how much lateral or sideways deformation you're going to get. So any sort of large motion or sideways motion like that is going to cause that you're going to run into that limitation of that virtual contact plane.
Okay, thank you. And then next question is, can gap elements be used to model ropes, cables, or strapping?
Yes, you can definitely use that. That'd be the opposite of the presentation here, but you can definitely use them in tension-only situations. They work just fine for that, as far as I can tell, from my couple exercises I've done in it.
All right, then it looks like that is it for the questions.